In the last lecture, we had started examining unidirectional transport in a curvilinear coordinate system. Okay. As I had said, in many practical applications, there are geometries in which the surface of the geometry is a curved surface. Okay. For example, the surface of the cylinder or the surface of a sphere. And if I have to solve a problem in which some boundary condition is specified on the surface of this on the boundary of this curved surface, then the boundary condition has to be applied at a curved surface. And the curved surface for a cylinder in a Cartesian coordinate system is where y square plus z square is a constant. In a spherical coordinate system, if your origin is at the center of the sphere, this is x square plus y square plus z square is equal to a constant. And therefore, the description of the boundary becomes more complicated, whereas in a Cartesian coordinate system, the boundary was at surfaces of constant coordinate. Therefore, in curvilinear coordinate systems, it is preferable to define the boundaries at surfaces of constant coordinate, okay, so that the boundary condition can be applied at a fixed value of that coordinate. And we had looked at one particular coordinate system in the last lecture, the cylindrical coordinate system, which is axisymmetric. And in the cylindrical coordinate system, the coordinate is actually the distance from the axis of the cylinder, that is r. R is the distance from the axis of the cylinder. Okay. And in order to determine conservation equations in this cylindrical coordinate system, we have to select surfaces which are surfaces of constant r. And the volume has to be the differential volume for which we do the balance has to be a volume that is bounded by two surfaces of constant coordinate. In this case, r plus delta r and r. So, it is an annular surface, inner radius r, outer radius r plus delta r and height delta z. Okay. So, that is the volume for which we will be doing a balance, and we will assume that the variation is only in the r direction. Okay. In that case, the inner surface has surface area 2 pi r delta z, the outer surface has area 2 pi into r plus delta r into delta z, and this is the volume. And we had derived the balance equation. Change in energy in a time delta t is equal to energy in flux at the inner surface times the area of the inner surface minus energy out, flux at the outer surface times the area of the outer surface plus the source times the volume times delta t. Divide throughout by volume, divide throughout by delta t, take the limit as volume goes to 0 and delta t goes to 0, and you get an equation that looks like this, where Qr is the flux and Qr is equal to minus k times the derivative of the temperature with respect to r, and substitute that, and this is the resulting equation. Okay. And if the thermal diffusivity is a constant, you can take the thermal diffusivity out. Okay. And as I had pointed out last time, the derivative in this operator looks something like this. Okay. It actually has a more complicated form than the simple second derivative that we had. Okay. The simple second derivative that we had in a Cartesian coordinate system. So, we have to solve this modified equation in the r direction in order to find out what is the temperature field. This equation can be derived also for mass transport. In that case, instead of I will have the concentration instead of rho Cpt and the mass diffusion coefficient d instead of the thermal diffusion coefficient, the mass source S instead of the energy source. And the equation that I will get is partial C by partial T is equal to 1 by r d by dr of d times r times partial C by partial r plus mass source S. Okay. If I write it in terms of the flux, I would get partial C by partial T is equal to minus 1 by R d by dr of R J R. J R is the mass flux in the R direction, just as Q R was the heat flux in the R direction. Okay. So, this let me just change the order. So, I will just write this as with a negative sign. Substitute the constitutive relation, I will get here d times partial C by partial R. Okay. Substitute the constitutive relation, this is what I will get, and if the diffusion coefficient is a constant, I can take that out and I will get partial C by partial T is equal to d by R. So, that is for the concentration field. Just substitute d for alpha, C for T and S instead of the energy source by rho Cp, okay, and you get these equations. That is for mass transfer. Okay. What about for momentum transfer? Okay. In this case, one can consider two different configurations. Okay, one can consider two different configurations. Okay. If you recall, when we had earlier done the momentum transfer in a channel, right, this was the x direction in the z direction and we had taken the velocity in the x direction. Okay, we had taken the velocity in the x direction, that is, this was the velocity Vx. Okay. And we were examining the transport of x momentum in the z direction. So, x was the direction of momentum, z was the direction of momentum transport. Okay. And the direction of momentum was perpendicular to the direction of momentum transport. When the direction of momentum is the same as the direction of momentum transport, there is an additional effect that appears and that is pressure. Okay. So, in that case it is slightly more complicated and we will see that in the following lectures, how does pressure affect momentum transport. But so far we have been considering cases where the direction of momentum is perpendicular to the direction of momentum transport. Okay. Therefore, we had written the stress tau xz is equal to mu times partial Vx by partial z. Okay. Tau xz is the transport of x momentum in the z direction, okay, per unit area, okay, per unit time, okay, force per unit area, that is momentum transport per unit area per unit time, transport of x momentum in the z direction. Okay. In this particular case, for the cylindrical coordinate system that we are choosing, right, the direction of transport is the r direction. Okay. Because we assume that the r direction is the direction in which there is variation. We have assumed that the r direction is the direction in which there is a variation of the temperature, concentration or velocity. Therefore, the direction for transport of momentum is the r direction. Okay. And perpendicular to the r direction, there are two other directions. Okay. So, the first one is r is horizontal in this left figure. The perpendicular direction is z. Okay. So, one could for example consider the transport of z momentum in the r direction, okay, because that is perpendicular to r. Okay. So, in that case one would for example get a velocity profile that looks something like this. Okay. The transport of z momentum in the r direction, okay, and write a balance equation for that. Okay. Let me see. let me call this as x now. Okay. So, let me not call it as z, I will call it as x for consistency. So, that later on we have consistency when we talk about fluid flows. Okay. I will call the axial direction as x in this case. So, one can have the transfer of x momentum in the radial direction, which is perpendicular to the x direction. Okay. The transfer of x momentum in the r direction. Okay. In that case, the balance equation, okay, is of the form of the same form that we got earlier. Okay. Rho times partial Vx by partial t is equal to 1 by r d by dr of r tau x r, okay, plus the body force, okay, where tau x r is equal to force per area in x direction at surface with outward perpendicular in r direction. Or if I say it the other way, it is the rate of transport of x momentum per unit area. Okay, so rate of transport of x momentum in r direction, okay, per area per time. Okay. So, this is the stress tau x r is the rate of transport of x momentum in the r direction, or force per unit area in the x direction acting at a surface whose unit normal is in the r direction. Okay. So, that is going to be the balance condition for the x momentum, for the momentum along the axis of the cylinder. Okay. So, this is going to be the balance equation for the momentum along the axis of the cylinder, and from the Newton's law of viscosity, this is going to be equal to mu times partial Vx by partial r. Okay. That is going to be equal to the expression for the stress. Positive sign in this case because I am considering momentum. For mass and heat flux, it would have been a negative sign. Okay. So, I substitute that into this equation and I get the balance equation rho times partial Vx by partial t is equal to 1 by r d by dr of r mu partial Vx by partial r plus Fx. Fx is the force density, the force per unit area in the r direction. Okay. Fx is the force density, the force per unit area in the r direction. For an incompressible flow where the density is a constant, I can divide throughout by density. Okay. I can divide throughout by density and I will get a mu by rho here, which is the kinematic viscosity. Okay. If I divide throughout by density, I will get mu by rho on the left side and I will get Fx by rho on the right hand side. Okay. And if the kinematic viscosity is a constant, it is independent of position, then my conservation equation becomes partial Vx by partial t is equal to nu by r d by dr of r partial Vx by partial r plus Fx by rho. Okay. So, you can see that this has exactly the same form as this equation, okay, as these equations. Okay. It has exactly the same form as the equation for the concentration and the temperature fields. Okay. Substitute Vx for C and nu for D and you get this equation. So, that is when the velocity is in the x direction. Okay. You could have another component of the velocity in this particular case, and that is when it is in the going around the axis. Okay. So, let me just illustrate that. Okay. If I had a configuration where a cylindrical configuration, this was r, okay, and this was the axis. Okay. I could have velocity going around the axis. Okay. I could have a component of the velocity going around the axis. Okay. So, if I looked at it from above, for example, if I looked at it from above, for example, the fluid streamlines would go around the axis like this. Okay. So, and this is what is called, as I told you earlier, this angle around the axis is what is called phi. Okay. This angle around the axis is what is called the phi direction. So, basically you have circular streamlines going around the axis. That is also perpendicular to the r direction, because r is radially outward, whereas these are circular streamlines going around the axis. Okay. In this case, the conservation equations are slightly different. Okay. The equation for the stress, okay, the equation for the stress is given by rate of transport of momentum in phi momentum, that is momentum is in the phi direction around the axis. Transport of phi momentum, momentum is along the phi direction, it is around the axis. That momentum is transported in the radial direction, okay, in this flow, okay, because there is a radial variation of the velocity. There is a radial variation of the velocity, therefore, the phi momentum is being transported in the radial r direction. This stress, force per unit area in the phi direction. Okay. So, if I take some differential volume, okay, so if this is the origin, this is at r, okay, and I have a differential volume between r and r plus delta r. Okay. Let us assume that this is delta r. Okay. This is the direction of the momentum. The direction of the momentum is along the circles around the axis. Okay. That is the phi momentum, the momentum in the phi direction, that is diffusing in the radial direction. So, the force per unit area in the phi direction exerted at a surface whose unit normal is in the r direction is tau phi r. Okay. Or the rate of transport of phi momentum in the, or the flux of phi momentum in the r direction. In this particular case, the constitutive relation is slightly more complicated. Okay. Tau phi r is actually equal to mu into partial v phi by partial r minus v phi by r, okay, for these kinds of circulating flows. Okay. It is not just the first derivative. Okay. The constitutive relation is quite is slightly complicated. The reason for that, which is outside the scope of this course, is that the unit vector in the phi direction is a function of position. So, even if you travel along a circle, even if the velocity is the same, there is still an acceleration because the direction of the velocity is changing. Okay. So, basically the direction of the unit vector changes with position, and because of that you get a dependence of the stress is given even if the velocity does not vary with r, you still get a dependence of stress, okay, on the phi coordinate. Okay. So, this is the expression for the stress, and the conservation equation becomes rho times partial v phi by partial t is equal to mu into d by dr of 1 by r d by dr of r v phi, okay, plus f phi. Okay. Note that the form of this operator is slightly different from what we had for the axial coordinate. Okay. There we had rho times partial Vx by partial t is equal to mu by r plus fx. Okay. That was the form that we had. Okay. So, this you can easily see that this operator is slightly different from this operator. Okay. So, that has to be kept in mind when we are writing balance equation for curved streamlines. Okay. So, when we write balance equation for curved streamlines, we have to keep this difference in mind. The derivation of this is not within the scope of this course, so I will not go through it. All I will do is to present the equations and the stress in this coordinate system. Okay. So, in this coordinate system, the equation and the stress have a slightly different form. Okay. So, that just to make you aware that along the phi direction we cannot use the same conservation equations that we had derived earlier for the r direction for the x direction velocity, okay, for momentum transport. Okay. We will see some examples of this. So, now that we have got the conservation equations, okay, we can then start to consider problems in steady state transport. Okay. So, first let us consider steady solutions. Okay. In cylindrical coordinates. Okay. The simplest problem that we can consider is the heat conduction in an annulus between two cylinders, okay, of inner radius r I, outer radius r O. Okay. The heat conduction with temperature T O on the outer surface and temperature T I on the inner surface. Okay. This is like heat transfer from a pipe, for example, the pipe of a finite thickness, inner radius r I and outer radius r O. Okay. And so, we have to solve the equation, steady state equation. Okay. If we assume that the conductivity is a constant, then this equation is k by r d by dr of r partial t by partial r. Okay. In this case, since it is steady, the temperature depends only upon r, and I can use total derivatives. Is equal to 0. Okay. This has to be solved subject to the boundary conditions r is equal to, sorry, okay. So, subject to those boundary conditions, we need to solve this equation and find out what is the heat transfer rate. Okay. What is the heat transfer rate due to this temperature difference between the inner and the outer surfaces. Okay. So, that is what we have to find out. Note that unlike in a Cartesian coordinate system, we cannot just shift the radius by a constant value, because the radius is the distance from the axis. Okay. So, it is not translationally invariant. Okay. If you change the radius, you will change the surface area as well. Okay. So, in this case, you do not have a translationally invariant way of changing the coordinates between 0 and 1. Okay. What we can do is to define the scaled radius as r star is equal to, you can take either one, either the inner or the outer radius. Okay. And I can define the temperature as T star is equal to T minus T I by outer temperature minus inner temperature. Okay. I can define that as the scale temperature. Okay. That would imply that the boundary conditions are T star is equal to 0 at r star equals 1, okay, and T star equals 1 at r star is equal to Rho by Ri. Okay, when r is equal to the outer radius, then r star is equal to Rho by Ri. Okay. And I can, since it is equal to 0, I can divide throughout by k and scale the coordinates, and my equation becomes 1 by r star d by d r star of this is equal to 0. Integrated one time, r star dt by dr star is equal to a. Okay. Divide throughout by r and you will get dt by dr is equal to a by r. Okay. Integrate it a second time, okay, where a is the integration constant for the first integration. Integrate it a second time and I will get t star is equal to a times the natural log of r plus the second integration constant b. That is the equation for the temperature field. Okay. And then I apply boundary conditions. Okay. First is T star is equal to 0 at R star is equal to 1. Okay. At the inner cylinder, T star is equal to 0. At R is equal to 1, the natural logarithm is 0. Okay. This implies that B is equal to 0. Okay. Because the natural logarithm is 0 at R star is equal to 1. Therefore, the solution of this is just that B is equal to 0. Also, T star is equal to 1 at R star is equal to Rho by Ri. Okay. T star is equal to 1 at R star is equal to Rho by Ri, and we already know that B is equal to 0. Therefore, this gives us a solution A is equal to 1 by natural log of Rho by. Okay. So, that is the final solution, okay, for the temperature field. Okay. Therefore, the final solution for the temperature field is that T star is equal to the log of R star by the natural log of Rho by. This satisfies the equation and it also satisfies the boundary condition, okay, that at R star is equal to 1, T star is equal to log of Rho by Ri. Okay. We can calculate the flux, okay. QR, okay, is equal to minus K times partial T by partial R. T is equal to, okay, from this equation, okay, I can write that, okay, T is equal to T star into To minus Ti plus Ti. Okay. Therefore, the derivative of T is equal to partial T star by partial R. And I have scaled R by the inner radius. Okay. I have scaled R here by the inner radius. Okay. Therefore, this is equal to minus K into To minus Ti by Ri partial T star by partial R star. Okay. T star is equal to R star A times log R star. Okay. So, this derivative just becomes equal to minus K into T O minus T I by R I, okay, into log of R O by R I into R star. Okay. Derivative of log R with respect to R is 1 over R, okay, and R star is equal to R by R I. Okay, is the ratio of the radius and the inner radius. Okay, therefore, R star times R I is just equal to R times log. Okay. So, this is the solution for the heat flux. Okay. From this, now we have to get a solution for the heat transfer rate and then use that in order to calculate what is the total heat transfer rate for a given temperature difference. This I will continue in the next lecture for the steady temperature distributions. I will see you then.